All right, so a few more simple problems with force, magnetic force equation. So F equals Q times V cross B, or for the magnitude F equals QVB sine of the angle theta, where remember that theta is the angle between V vector and B vector. All right, and the problem that I'm looking at is on page 826. It's number 27. This is in the book for algebra-based physics. But it is an interesting problem worth seeing, I think. So if you have the book in front of you, you can read the problem, and if you don't, you can deduce what's happening from the from what's about to see. So you have a microwave here, like a microwave that you have in a kitchen. All right, to make the long story short, you'll have some stuff here, but to make the long story short, on the inside of this microwave, somewhere in this section here, on the inside, you will have a device that is called a magnetron. So on the inside here, you will have a device. I'm just going to draw it like tube, and I'm going to call this thing magnetron. And to make the long story short, what this thing does is it shoots electrons into a magnetic field, and it causes. So let's say that let's draw this. So let's say that we have a magnetic field that points. Well, let's say that the magnetic field on the inside here, as you look at this thing, points into the page. You have some permanent magnets in there that set up this strong magnetic field, constant, steady, strong magnetic field. And let's say that it points into the page on the, and this magnetic field would be on the inside of this magnetron. And we have the magnetic field set up by some magnets there, and then you take an electron and you shoot an electron into this magnetic field. Now, let's just think about this, because I want this thing to do something very specific. So let's say we shoot an electron into this thing at this point. Here's an electron. So here's Q, has a negative charge, and we shoot this at this point with a velocity v that points like this. And then what this thing will do is it is going to generate a force. Use the right-hand rule. By now you should know how to use this. Use the right-hand rule to figure out the direction of the force. Well, if the magnetic field points into the page and the velocity vector points to the right, then you would have the force from the right-hand rule pointing up. But because this is a negative particle, the force would switch the direction, and therefore it would point down the page. So this would be force F. And let's pause here for a second, because we want to analyze this thing. So if this is the case, then this particle, this electron, wouldn't be able to continue to move in a straight line here, because there's a force that points downwards. In other words, this electron would have to curve because of the presence of this force. So it would curve a little. Maybe it would end up somewhere over here. And when it's at this point here, this velocity vector would then point like that. And if there were no force acting on this electron continue along the straight line here, along the line in which the velocity vector points. But there's going to be a force in it, and you can determine the direction of this force using right-hand rule. And if you do that, you will see that the force is going to point. So again, take your fingers of the right hand, make them point into the page, the direction in which the magnetic field points. And then make sure that the thumb points in the direction of the velocity vector. And then you find a specific direction. But remember, this is negatively charged particle, so you flip the direction of the force. And so you'd find that the force points like this. Here's force F. And that implies that this electron cannot move along this velocity path because of the presence of the force. And so it will have to curve a little. So it's going to change its direction, and maybe now it will end up somewhere over here. So here's a negatively charged particle. moving with a velocity v like this. If there's no magnetic field present, then this thing will continue along this straight path. But let's say that the magnetic field continues to be present here. Let's extend this magnetic field. And let's try to figure out the direction of the force on this electron as it's moving here at velocity, with velocity v. So the force would point like this. Use the right hand, determine this, and that implies that this electron is not going to move in a straight path, but rather it is going to change its direction, and it will end up somewhere over here. And I think you get the picture of the velocity points like that. To redraw this, if you have a magnetic field, I want to use blue. If you have a magnetic field and the magnetic field points like this, and then you shoot an electron into this magnetic field, if you shoot an electron like this, with a velocity v, this electron will just follow a circular path. And when it gets back here, it will just exit out. Now in a microwave, in a magnetron, we use the same idea to cause this electron to move around in a circle. So in a microwave, on the inside of this magnetron, which is on the inside of the microwave, there's a magnetic field, and we shoot electrons into this magnetic field, and electrons move in circles. Now you don't know this yet, but if you take an electron and you make it move in a circle, well, you actually know this. If you have any object that moves in a circle, then there's going to be an acceleration associated with it. So this implies that there is a centripetal acceleration present, and you can calculate the centripetal acceleration. It would just be v squared over r, where r would be the radius of this circle here. All right, now what you don't know is that if a charged particle is moving with some acceleration, so if a q moves with some acceleration a, then you will start emitting electromagnetic waves. You will get electromagnetic waves out of it. Why that's the case, that's a separate story, but you do need this to understand the problem. And so what we have is that we shoot an electron into a magnetic field, it moves in a circle, and it emits electromagnetic waves. And it is these electromagnetic waves that are emitted from the magnetron that then travel into this chamber where you have the food. And these electromagnetic waves heat up your food, which is in the microwave. Okay, now let's try to solve the problem, see what the problem actually gives you, what it doesn't give you, and what it asks for. It gives you the frequency of, see what it says. Electrons orbit in the magnetic field at a frequency of 2.4. So we know the frequency of the orbit here. It's 2.4 gigahertz. That means that the electron moves 2.4 one second, what's giga? I gotta look up giga. So giga means 10 to the 9th, and that implies that F is 2.4 times 10 to the 9th hertz. And what this means is that this electron moves 2.4 times 10 to the 9th times every second, moves in a circular path. So the circle is completed 2.4 times 10 to the 9th every second. That's a lot of times. And this generates then an electromagnetic waves that has the frequency of 2.4 times 10 to the 9th hertz. Anyways, the frequency is given to us. So we have the frequency. And that actually is all we have. And the question is, if that is the case, if this electron here, this is an electron, if this electron moves at this frequency, has this frequency here, what is the strength of the magnetic field? So you're actually asked to calculate the magnetic field on the inside of the microwave. Well, I wanted this in blue. That did not work out. Here's blue. The question mark. All right, so this is the problem you're looking at. What is the magnetic field in a magnetron inside of the microwave, given the fact that the electron must have a frequency of 2.4 times 10 to the 9th hertz? You can pause the video and see if you can figure this out by yourself. And in the meantime, I'm going to start. So I'm looking for the magnetic field, and chances are I will have to use the force equation. F equals Q times V times B times the sine of the angle theta. Now the force that acts here on this charged particle points towards the center, so this is the force, the magnetic force, and so from here it's easy. Well, anyways, keep that in mind, but what I need is the angle theta, and angle theta is the angle between vector V and vector B. Now vector B points into the page, vector V points to the right, so the angle between the two is 90. And so this here implies that the angle is 90 degrees, right? The magnetic field points into the page, magnetic field points into the page, that's B, and then the velocity vector points to the right, that there is 90 degrees between these two. So I can rewrite this equation as F equals Q times V times B times 1, because sine of 90 is just 1. So I know Q. I'm looking for B. So what I have is F equals Q times V equals B. Now I know Q, so what I need to figure out is F and B. And then I have B, and I'm after B. So this F, the magnetic force in this case, that F is just the centripetal force. The centripetal force, because this magnetic force is the force that sets up the circular motion. And the expression for the centripetal force is mass times the centripetal acceleration. And this would be the mass of the electron, because that's the thing that moves in a circle. I would have here mass of the electron times AC, and AC by definition is just V squared over R. So let's plug this in. What I will have here is mass of the electron, which I know, I can look this up, times V squared over R. I'm going to put here over R, and then I have Q times V. So I get, and this equals V. So this cancels, that cancels, and I end up with mass of the electron times V over Q times R equals V. Well, that didn't really help because I don't have V and I don't have R, but I do have this frequency. If I have frequency, I can easily figure out the period, because period is just 1 over the frequency. So let's do that. 1 divided by 2.4 times 10 to the 9th. Let's see what we get for that. So 2.4 times 10 to the negative, no, times 10 to the 9th. Then we flip this. So we get 4.2 times 10 to the negative 10th seconds. This is how long it will take for the electron to orbit once. And if that is the, and then V equals the speed at which this thing is going to fly around is going to be equal to the circumference divided by the circumference divided by the time it takes to fly around the circumference, which is big T, the period. And so of course that would be 2 pi times R, that's the circumference, divided by T, which I know that's 4.2 times 10 to the negative 10th. So I can now take this expression here and I can plug it in into, so I can take this and I can plug it in here. All right, so let's move this up. And now what I get is that mass of the electron times V, well, not times, I want to substitute for V, times 2 pi times R divided by, let's just put T for the moment, period. So this is V divided by Q times R equals V. Now R will cancel, and so what I have is that well, actually I'm done at this point, because this gives me the magnetic field as the expression for the magnetic field would be the mass of the electron times 2 pi divided by the charge of the electron times the period. And I have all of the needed numbers. So I can now substitute the actual numbers, and I can have my solution. So let's maybe do it. Let's move this whole thing to the right, the left, and then let's plug in the numbers. Mass of the electron, that's 9.1, or at least I think that's what it was, times 10 to the negative 31st times 2 pi divided by the charge of the electron, which is 1.6, times 10 to the minus 19th times t, which is the period, and we figured this out as 4.2 times 10 to the minus 10th. And this equals 0.085 Teslas. That's the magnetic field on the inside of the microwave. Okay,